Okay, so this is the last video of the spring semester of 2020, and here I have just a couple concluding remarks about hypothesis tests before we wrap things up. So before we talk about page 163, I want to refer back to what we did on page 153, where we looked at this hypothesis from our first example, where p equaled 0.35 was the null and the alternative p less than 0.35 with a sample percentage of 0.27. And we looked at that same result, the 0.27, and how changing the sample size from 100 to 200 to 600 changed the p-value. So the p-value is not affected just by the sample results, but also by the sample size. And as n increased, the p-value decreased. And here on this page 163, we're going to look at more about that same idea. So, big important thing here is that statistical significance is not the same as practical importance. Just because something is statistically significant does not mean it's practically important. So large samples can detect small differences very accurately. We saw that as the sample size got larger, the p-value got smaller. These small differences may not be practically important. So for our example, suppose instead we had an n of 10,000, but the sample percentage was 34% instead of 27%. So that would be only 1% less than the percentage in the null hypothesis. If that was the case, but we had such a huge sample size, our test statistic would be minus 2.10, and our p-value would be 0.0179. And at the 5% significance level, we would reject the null hypothesis. But if the difference is only 1% less, is that a practically important difference? Okay. It may not be, even though you have a small p-value. So this doesn't mean that large samples are bad. Okay. It does, however, mean that you should think about practical importance as a separate issue from statistical significance. And that would be up to the people who have knowledge in that discipline or field. The p-value is only measuring the probability of seeing those sample results. It doesn't put that probability in context. So also recall that when we had n equals 75, which is a fairly small sample size for measuring percentages, our sample percentage was 27%, so that seems like a fairly large difference from 35%. But with such a small sample size, our p-value was 7%, and it was not statistically significant. So the other side of the coin from large samples detecting small differences very accurately is that small samples can fail to detect differences that may be practically important. So if there's a difference that a researcher believes is practically important, but but the p-value was still large, it's because they didn't have a large enough sample size to detect what they feel is a practically important difference. So the better approach is for the researcher to determine what is practically important and make sure that they have a large enough sample size to be able to detect that difference. So I'm going to skip ahead to page 168 and talk about multiple hypothesis tests and then come back to page 165. So remember that choosing a significance level of 5% means you will reject the null 5% of the time when it's true. So suppose you collect data using a questionnaire with 20 questions. And if you do 20 separate hypothesis tests, one for each question, at a significance level of 5%, suppose the null was true in each case, and the null was true for all 20 tests, you would expect to reject the null in one of those 20 cases. That's a typo there, that 5 should be a 1. So just by chance. So you can't really say that, well, in 19 tests, the results were not statistically significant, and in one, they were statistically significant, when, if you do 20 tests, that's what you would expect to see just by chance. So if you want to do multiple tests and make multiple conclusions simultaneously, the procedure must be altered by lowering the p-value cutoff. So the simplest way to do this, and we're not going to cover this in this class, but should you ever want to do this at some point in the future, the simplest way to do it is by using something called the Bonferroni correction, which says you simply divide the significance level by the number of tests you want to do. So if you were going to do 20 tests, you would divide 0.05 by 20 if testing at the 5% significance level. And so you would compare your p-values to 0.0025 instead of 5%. And then you could collectively make those 20 conclusions at the 5% level. So at this point, you should pause the video and read pages 164 to pages 167, unless you've already done that. So in recent years, there's been a lot of controversy about the use of p-values and their place in scientific research. And a lot of that has stemmed from the misinterpretation and incorrectly assigning the p-values more prominence in the interpretation of the results of a study than they should have. So in 2016, so 3 years ago, the American Statistical Association came out with this public statement about the use of p-values in evaluating research. So the validity of scientific conclusions, including whether or not they're reproducible, depends on more than the statistical methods themselves. And by that it means more than the calculation of the p-value. We've only looked at the two simplest situations, but things get much more complex, and the situation dictates which technique you're going to use. So the validity of those conclusions depends on the fact that the appropriate technique for analyzing the data was chosen, properly conducted analysis, meaning everything was calculated correctly, and the correct interpretation of the statistical results also play a key role in ensuring that the conclusions are sound. So they start off by talking about what is a p-value, which we've been talking about repeatedly in all our examples. They give the same definition that we used. By under a specified statistical model, they mean if the null is true. And by statistical summary, they mean sample statistics. So p-values can indicate how incompatible the data are with a specified statistical model, i.e. the null hypothesis. They do not measure the probability that the studied hypothesis is true or the probability that the data were produced by random chance alone. And scientific conclusions and business or policy decisions should not be based only on whether the p-value passes a specific threshold, i.e., is it the p-value less than 5%? So this kind of blind adherence to 5%, particularly 5%, which is just often used only because it's the most common thing that's used. So treating that as if that's the magic line between right and wrong is just never how the people who came up with this in the first place ever intended p-values to be used. So researchers need to bring many contextual factors into play. Just the knowledge of the discipline, the area in which the data is gathered, the design of the study, the quality of the measurements, the external evidence that already exists, the validity of the assumptions. So all that plays a role, or should play a role. So while often final decisions do require some sort of yes, no, thumbs up, thumbs down decision, that does not mean that the p-value alone can ensure that that decision is either correct or incorrect. It's one tool to use in your decision making. And proper inference requires full reporting and transparency. And this is getting to the idea that we just talked about on the previous page when doing multiple tests on the same data, essentially. So conducting multiple analysis of the data and reporting only those with certain p-values. So just reporting the p-values that you found to be significant without reporting that you did all these other tests, cherry picking the good ones, is known as a bunch of terms refer to that: data dredging, significance chasing, like chasing the ambulance, significance questing, selective inference, selecting only the good ones, and p-hacking, meaning looking at the p-values and then deciding what you want to report. So that's basically cheating. It's not statistically sound, and it's this kind of abuse of statistics that can give statistics a bad reputation. And their fifth point is that a p-value does not measure the size of an effect or the importance of the result. So this is what we just looked at previously. We saw that we could have a larger difference and get a smaller p-value versus a smaller difference and get a larger p-value depending on the size of the sample. So it's not the size of the effect, and it does not measure the importance of that result. Any effect, no matter how tiny, can produce a small p-value if the sample size or measurement precision is high enough, and large effects may produce unimpressive p-values if the sample size is small. So on page 167, pretty much it is repeating the ideas from the previous pages. So this is the end of MAT 120, pandemic style. So use the next week to make sure that all your web assigns are done before the final. Also, watch your email for important announcements I'll be sending out about the final. That's it for tonight. Stay safe and stay well.